So the codeBruijn representation of syntax is a well-scoped representation of terms, except that instead of indexing terms by the scope of variables that they are permitted to use, we index them over precisely the support of variables that they actually use. So doing this involves maintaining exactly the kinds of gnarly invariants that you better have a type checker kicking your arse about. Right. One reason why this kind of representation just, only very, very brave people play these sorts of games, maintaining the invariants by hand. Right. Once things get sufficiently intricate, if you, it really helps to have a machine force you to get stuff right. So, a relevant plan.
Silly question. Does codeBruijn has a formal meaning? I mean, does the co have a formal meaning?
Well, how formal it is open to dispute. I'll go there. So the thing about the Bruijn indices, where you represent variables by an initial segment of the natural numbers, however many are in scope, is that you only throw variables out of scope by deciding to use one of them and not the others. That's to say, expunging from scope happens at a canonical place, namely the leaves of the syntax tree. In the codeBruijn representation, a canonical representative of the alpha equivalence class is chosen by expunging variables from scope as near to the root of the tree as possible. So the moment a variable stops being used, if there's some region of the syntax tree in which a variable is not used, it gets kicked out of scope before you even get there. And in particular, we have two forms for abstraction. We have the relevant lambda, so that's to say, which lambda says, I am bringing this variable into scope and I promise to use it at least once. And there's a separate, explicitly vacuous abstraction where you say, this is the place where I'm allowed to bind a variable, but I'm not even going to bother because I'm not going to use it. So that's to say, if you're not going to use the bound variable, it doesn't even come into scope, let alone anything else. So we're keeping real tight handle on the supports of terms. And then what is a relevant substitution? The relevant substitution has a source support of the variables that are going to get substituted, and a target support of variables, each of which is used in at least one substitution image of the source variables. So each source variable has an image term, and all the target variables get used in at least one image. They all show up somewhere. So you would expect that if you apply a relevant substitution with source support and target support to a term relevant in the source support, as all the source variables get used at least once, you're going to substitute all of the images at least once, so all the target variables will get used at least once, and the support will behave compositionally on the nose. Of course, this is what happens. we'll see what that, how these jigsaw pieces fit together, hopefully, as things unfold. Okay, so the key thing that happens anywhere a term has two subterms, there is a distinct possibility that some variables may not be used in the left subterm, and some variables may not be used in the right subterm. So at that point, we have to restrict the variables available to those which are actually going to get used on the left and on the right. So we need to talk about selections from some available bunch of things. And that's where the thinnings, or rather, so selections, so thinnings are order preserving injections. Selections are opt thinnings. Right. Another way of looking at thinnings is that they are bit vectors. Here's a bit vector indexed by length and population count. So a bit vector, length 5 with 3 ones in it, is explaining which 3 of 5 things are being selected. These things, so that's to say, well, actually, I'm not going to do it with numbers. I'm going to do it with lists. Numbers are just boring lists. Right. Right. So what's going to happen? And I'm going to do this highly generically. So fix S the set of term sorts. So maybe if you were doing something like untyped lambda terms or something like that, then S will just be unique. But you might have multiple syntactic categories on the go, or you might be doing something like simply typed lambda terms, where you might identify the sorts of terms with the actual types that you're using in the type system of the language you're modeling. Got a set of term sorts, and then a scope is some gamma in words over term sorts, which we shall, of course, think of as snot lists, because we're accustomed to growing scope. We're accustomed to the right-hand end being the local end. So these things grow on the right. So the objects of this category are the scopes, or rather the supports, I should say. Supports. Right, and how do we generate these things? The empty thinning, it explains how the empty word can be selected from the empty word. And if some thinning theta selects gamma from delta, then theta 1 selects gamma s from delta s. So if you see a 1 in your bit vector, that means choose this one. And if theta is in gamma selected from delta, then theta followed by 0 selects gamma from delta extended by S. This is explaining, though we're explaining how to choose some of the delta to get the gamma, and the ones in the bit vector tell us how to find the gamma that we're selecting from the delta which are available. So this is a perfectly sensible inductive definition if your programming language can go with indexing. Those are how the thinnings are generated. And then, of course, if I want a category, I have to say what the identity is and what the composition is. So I think I just about have space to do that. The identity for the empty is empty. The identity for gamma S is the identity for gamma, followed by 1, right? The identity thinning or selection is the full ones that select all the things. And then how does composition work? I'm going to write that as a semicolon. Theta followed by phi throw away is theta phi throw away. Or we could have theta 0 phi 1, and that's still going to get thrown away. But if the front and the back both agree, we're actually going to keep the thing. And if we're empty, we get empty. Okay, now, bit of dependently typed programming, tradecraft. It's a really, really good idea not to define this operation directly, but rather to define the three-place relation that is the graph of this thing. So that is to say, we say what it is to be a composition triangle, right? So for us, we will have data types which represent pictures which look like this. This is some theta, some phi, some psi, and we will have, and we really want to represent the proposition that theta then phi is psi, that we have a composition triangle. And that's just given by defining inductively the graph of this relation. You can separately show that given theta and phi, which fit together in the middle, there is such a psi, there's a unique psi such that the triangle exists. And why do we want to do that? Well, if you have something like a commuting square, how do you talk about it in a dependently typed programming situation? You might say theta then phi is phi prime then theta prime. Might have, if you you might have an equational hypothesis like this, which says that the two outputs of these composition functions coincide. And then you ask, how the hell do you make the slightest bit of use of this assumption? I mean, you know, it's a complete disaster. You've got two outputs that are coinciding, And the only thing you're able to poke are the inputs. So you end up having to reason about the individual thinnings that make up this picture, instead of about the picture as a whole. So not a good idea to have these equations kicking around with that composition operator. Altogether better to have the inductive representations of two triangles which share a side. Right? That's to say, what we are doing by triangulating explicitly is to get rid of green slime. So working with the triangulated presentation of the equation is real nice, and associativity is lots of fun. You can represent associativity as completing a tetrahedron. It's also kind of nice that if you think about this picture, then there are some missing edges. And associativity is equivalently that you have two of the blue arrows, but not the third, and the two triangles made by the two blue arrows. And given this information, you can compute the missing blue arrow and the other two triangles. You see there are four triangles in this picture. So those presentations of associativity are equivalent. If you've got one for for this, when this blue arrow is missing, you can extract the other ones. And it leads to a hilarious mode of doing theorem proving in AGDA, where you sit there with a massive context which says these points exist, these arrows exist between these points, these triangles exist between three of these arrows. You look at this context, and it's just ASCII salad, right? What you end up having to do is, get the back of an envelope and a pencil and actually draw the diagram that's being textually listed. Bits are being listed in this context, and then you can see what you're doing. But the program itself is just complete gibberish. It's easy to do if you've got the pictures. It's just completely impossible to read afterwards unless you reproduce the translation. Okay, so this is what's going on in the category of thinnings, which of course is also basically it's Pascal's triangle turned into a type that actually you're not just counting the number of making the selection, you're actually representing exactly and once each the selections which are possible. So it's in the kind of ascent from the primordial slime, we began to achieve some kind of discrimination when we crossed out 1 and wrote 2 instead. Is it or isn't it? And then we achieved a greater level of sophistication when we crossed out 2 and wrote nat. So never mind whether there is one or isn't one, how many of them? And then, you know, we crossed out nat and wrote set. It's like, actually, what are they? And, you know, then we crossed out set and wrote cat because they also have structure. So there's a gradual, you know, gradual increase in sophistication going on there. Okay, so the other piece of equipment I will need for this job, yeah, one of these days I'll talk to you about patterns for which I will need codeBruijn, but I don't need codeBruijn today. I do need to know that whenever I have a picture like this, so that's to say I have 2 selections from the same support. You think of this is some gamma. This is, maybe we're building a pair of terms. And so this, these are the things that are in scope. These are the things that are actually used on the left. These are the things that actually occur on the right. We're going to want to make sure that we know how to compute the union of gamma L and gamma R, which will be some, we'll have some delta here. And I'm going to write this to say that these 2 thinnings cover their target. That's to say, they're bit vectors, and if you took their bitwise disjunction, you'd get all the ones. Right? So there's I mean, you can define that property inductively, as I did in my paper, Everybody's Got to Be Somewhere. But of course, you also get the universal property that if you have any 2 other thinnings that include gamma L and gamma R, then you can get from here to there. This is the smallest. This is this is the union. There's no junk. Okay, so these things are important, and they are again definable inductively. That's to say, we have all of these 2-dimensional structures, the composition triangles, and the covering proofs. I tend to call triangles V because they're pointy, and I tend to call covering proofs U because they're unions. But they're all represented inductively. So again, I spend my entire time just, you know, with Agda contexts telling me what the jigsaw pieces are, and constantly reconstructing the picture of the box. Okay. So we've got thinnings, we've got proofs that 2 thinnings cover their union. We've got the pieces we're going to need. Okay. So we've got, I'm going to define, just as a grammar, what it is to be an adicity. Because I'm going to build syntax generically. So I'm going to need to talk about things that are built up from stuff. So an adicity is either a term sort, or it's one or a pair of 2 other adicities, or it's a binding where the bound variable takes a term sort, and what's under the binder is some other adicity. So that enables us to talk about the payload of some lump of syntax. You know, it might just be a leaf, in which case its adicity will be 1. It might have a bunch of subterms, in which case you'll have a tuple, or why don't I just do it for the lambda calculus? Yes.
What's that word you're saying?
Adicity. As opposed, so adicity is the uncurried version of arity. Right? So something of arity 3 takes 3 inputs, something that is 3-adic takes a triple of inputs. Right. Okay. Yes, not to be confused with acidity. But an anagram thereof. Okay. So then what's the whole theory is going to be parameterized by some type constructor which says that for each term sort that you might want to build terms in, and each adicity of components you might build them from, which constructors do that for you? So let's have an example. Like an example, right? So e.g., if S is 1, then we might take lambda is in Couture singleton, arrow singleton, and application is in Couture singleton, paired with singleton. So that's just saying, yeah, this type says the ways of packing things up. So you can basically do multi-sorted syntax, and you can identify individual binding types.
That's similar to like nominal theories.
Well, it's not going to be very nominal the way I cook it, but I mean, so the whole point is there's nothing here that says what the representation of binding is going to be, just where a binding is expected. Right, so you could perfectly well take a description of a syntax in this way and interpret it with a de Bruijn interpretation. In fact, let's do that. Orange, of course. Right. So the idea is that we're going to interpret an adicity given, and that's going to give us some operation that maps, actually not sets to sets, but rather S star to set to S star to set. So that's to say, things which are indexed over, and here in the de Bruijn interpretation, these things will be scopes. What do you have? You have the interpretation of, actually no, this is just that's just a single sort, but we're going to get something scoped. So if we get a term sort, that's going to be T of S. Interpretation of 1 at anything is going to be the unit type. The interpretation of pairing is, you guessed it, the pairing of the interpretations. Oh, except that I should be writing gammas here. Paired with interpretation B, X, gamma. Sorry, my X's and my times are too similar. Maybe I'll write that as a multiplication. And then the interpretation of S, triangle A at X and gamma is the interpretation of A with X and gamma extended by S. You shove the variable binder straight into the context and off you go. And then what do you say? Well, this doesn't tell you how to build variables, but you can attach variables uniformly. And then you can take a fixed point with this. You can basically take a free monad over this thing and you get to some sort of syntax. You instantiate variables just by membership of gamma is how you get a variable of a given sort. By the way, the nice way to define list membership in this setting is as the special case of thinnings, where you have a singleton being selected. There's no need for a separate type of de Bruijn indices. Singleton thinnings just do the job. And moreover, have the benefit of inducing by blatant obviousness. The fact that thinnings, the fact that binding a variable is functorial as far as thinning is concerned. So context extension, scope extension, with the new source variable being mapped to the new target variable. It makes it's a functorial operation. It's a functor from thinnings to thinnings. That's kind of nice. So thinnings act on de Bruijn terms by post-composition at the leaves. And to go under a binder, to push a thinning under a binder, you just add an extra one on the end, saying there's a new bound variable in the source, but there's also a new bound variable in the target, and one's going to turn into the other. So that's nice, but it also illustrates the problem. So that is to say, the action of the functorial action of thinnings on de Bruijn terms that allows you to chuck in a bunch of variables you're not using is how the de Bruijn shift is accomplished. And the annoying thing is that it acts only at the leaves. Because de Bruijn indexed terms store their non-usage information in a particularly annoyingly inaccessible place, as far away from the root of the term as it's possible to be, you have to traverse the whole term, finding all the variable use sites in order to record that there are some more variables that you're not using. And this is why there's all this misery about defining substitution and renaming mutually and all the shenanigans people do to avoid that. And it's all because non-usage information is stored as far away from you where you'd like it as possible. So I'm going to do that. Let's figure out how to build terms. So I'm going to talk about terms of in general, they have an adicity and they are over some support. Okay, so this is the thing I'm now going to define. There is a variable it has its adicity must be a term sort. And what do you think its support is? Yeah. Singleton of exactly that. Of exactly that sort. That's to say, by the time you reach a variable use site, there is exactly one variable that has not been expunged from the support. The rest have all been discarded somewhere further out. So likewise, next base case, the singleton has adicity 1 and the empty support. So we're nailing this down. Then we also have C of t is in some term sort S support gamma if C is in vector SA and T is in A with what support? Well, there aren't any variable uses sitting inside the C, so they better all be in the T. Right. What happens next? Let's do binding. There's a lambda T which lives in S bound in an A over gamma, and that's allowed if the bound variable, the thing of sort S, we put it in the support because we're promising to use it. And then there's a variation on the same thing. The constant, which of course I write as kappa, says that yes, we could have bound a variable of type S, but as we're not going to use it, we're going to give something of adicity A without making any use of anything extra apart from the gamma that we're already promising. Okay, so these things, we can tell the difference immediately. Lambda says, I actually want that variable and I'm going to use it. And kappa says, don't even bother about that variable. Okay, all of which leaves us with the fun one, which is, I'm going to have things called T and V. Oh, I'm painting myself into a corner. I can write this down. So this is going to be in A cross B with support gamma. Well, let's do the easy bits. We better have T and B. And this is going to be A over gamma left and B over gamma right. And there had better be, well, I'll just draw the picture, shall I? the left thinning and a right thinning, and between them, they cover. So if you're a dependently typed program, you can get away with this, right? The two thetas are implicit because they're determined by the type of the covering information. And this is particularly delicious, especially if you were a programming language person at Edinburgh in the 90s. Because where are the bits in this part of the diagram? All right? The bits are in the bit vectors, in the thetas. The fact that the two things cover is a mere proposition about which we are explicit. So what we're doing in this style of working is that the data-free explanations are the things which we write about in the source code of our program. They will be thrown away by any decent compiler. They are not in the executable object code. Instead, what's actually needed at runtime are the thinnings, the bit vectors that tell you which things are actually being selected, and those are nowhere in sight as far as the source code is concerned. So what is happening is the upending of Milner's coincidence. We are writing explicitly an explanation that's going to be thrown away, and Agda's unification algorithm is figuring out what the actual program is. And really, I think it's much better that way. Okay, so those are codeBruijn terms. What are relevant substitutions? Nice thing is that, well, we can define a mapping from supports to adicities in what I hope is a reasonably obvious way. I'm going to say that the empty support, I'm going to write a green bar for convert to adicity on this slide only. That's the unit adicity, shock horror, and then this is gamma and some term sort S. How do I turn that into an adicity? Well, you guessed it. It's you just, as we've been doing forever, we interpret context-like things as left nested tuples. Okay, and from now on, I'm not going to involve. But yes, so a relevant substitution is some. Well, on this slide, I will. One of those. So that's to say, it is a tuple of images, one for each thing in gamma, and between them, all the variables of delta show up somewhere in that tuple. So we're enforcing the relevance property on the nodes. So the challenge then is how to define the actual action of these things. So now we need some operator, write it as a slash, which takes actually
something of any adicity over gamma, and something gamma to delta to A to delta. I'll write my green bar there, and some arrows. So that's to say is we've got some lump of syntax whose support is gamma. We've got a relevant substitution from gamma to delta. Delta is going to be on the nose, the exact support of the substitution image. Yeah?
Is that really the order in which you're writing the substitution and the thing in which you substitute?
I am a massive fan of diagrammatic everything.
Okay.
Yeah. So this is the thing being acted on. This is the thing doing the action. This is what comes out. Yes, and I would point out that A can in particular be something generated by the green bar operation from some other scope. So this thing is not only the action of relevant substitutions on terms, because relevant substitutions are terms, it's also composition of relevant substitutions. Okay. We're going to want to prove that that it absorbs identities and that this composition is associative. So of course, the thing I'm going to recommend that you do is not to define this function directly, but to define inductively the relation which is its graph. Because proving the associativity by induction over that relation will be one hell of a lot easier than kicking those functions until they compute. So yeah, message again is that we actually want to talk about the composition triangles, not the composition function. And then we show that if you give me these two things, I can give you that thing and the triangle that shows that the right thing has happened. So we're going to figure out what pieces we need to define the graph of this action. And some things are straightforward and others are not. Let's do some easy ones and then get to the right place. How much time have I got? Minus how many minutes?
5 to 10.
Okay, I'll just go straight to the difficult bit then. Right. Okay. We're trying to figure out how to process one of these things with some substitution sigma. And that's equal to what? Well, hidden in here is a left thinning and a right thinning. So we've got some substitution. I'm going to draw that as a wiggly line from gamma to delta. But what we need to act on T is not the whole of that substitution. Instead, we just need the parts of the substitution that are selected by theta left. So in particular, I am going to need substitution sigma left, which has as its target support. Well, since we're only selecting some of the input variables, we're not necessarily going to get all of the output variables. So we know there is going to be some target support for the left, and that will be a selection from the delta that we had available for processing the whole pair. So we arrive at these lovely little squares which have thinnings up the sides and relevant substitutions across the top, representing the assertion that if you chuck out these source variables, you recover the relevance of that substitution, because we love that word, don't we, by throwing away some of the target variables. So we end up, again, inductively defining what it is to be one of these squares. And we can show that these squares paste together in a sensible way, both vertically and horizontally. So if you refine it, if you make an even finer selection from gamma left, then you'll get an even finer selection from delta left. And then once you've actually got composition of substitutions, then these things will behave in a sensible way too. But yeah, I need to stop. So I'll just tell you what the key thing that you have to prove is to get any of this stuff to go through. And that's when you've got gamma left and gamma right, and you originally had a substitution that took you to delta, and you know that this covers. And what you know you're going to get from being able to construct these things is the other gable end. There will be a delta right and a sigma right. Oh, that should be wiggly. And a delta left and a sigma left. And these will be the two, this will be the substitution that you want to act on T, and sigma right will be the substitution that you want to act on V. And you know that the inputs form the covering. And what you have to prove is what I call, just because of the picture, the roof lemma, which says that if you started with the covering, you finish with the covering. And it turns out to be a whole bunch of tedious classical sequent calculus in Porphyrius junction. Literally, you just see, yes, you know, it was either on the left or on the right or both, you know, what the hell happened. So that gets us, so the roof lemma is what tells us that when we put all the pieces back together again, we haven't missed any of the variables. And it all goes through rather nicely, and it has one kind of cute little property. Right. Every time you go under a binder with a lambda, you extend the substitution, but you map the new source variable to the new target variable. So in that respect, the substitution that you're pushing along gets slightly more like the identity substitution. And every time you throw some stuff out when you make these selections, your substitution gets shorter. So it's at least more, you know, so if you actually end up throwing out all the images that aren't the variable you first thought of, again, the refined substitution is possibly a lot more like the identity substitution than the one you started with. So what you can do is test whether after each of these refinements, each of these selections, what you've ended up with is actually the identity substitution. Possibly even the empty substitution, because you're just dealing with a term that's closed. And then you don't even need to visit that entire subterm. You can just say, oh, I can see the substitution isn't doing anything, skip it. So that's where the scoping information, bothering to maintain the invariant, gives you opportunities
to say it work. But anyway, that's a construction which I'm hoping to write up real soon now with the title How to Do Something Relevant for a Change, and it's absolutely crucially based on the way these little things tell a story of selection from the source support inducing selection on the target support. The way these paste together horizontally, vertically, with the full double category story. That's the double, being a double category means they paste in both directions and you can interchange. Okay, I should probably stop now.